Yes, in here there are some another examples, but we can easily speed control of a DC motor. We can easily evaluate this part. This is a control block diagram of a DC motor for the speed control. In here we have a controller gain. For this system, the open loop transfer function is as like that. For the angular speed of the system, we can get this one. If the kt value is 1, we can easily say this. If we get here G1s, this system will be unity feedback system. Okay. For this system, this is the time constant of the system. Time constant of the system. And what can we say now? What is the time constant and controller gain? Here, these parameters are constant because these are system parameters, but here we have also controller gain. So, if the k value is increased, the time response of the system will be decreased. Okay, what does it mean? How fast the system responds to the input. Time response means as like that. Okay, and also we can say for the k value is positive k value, the system will always stable because time constant is positive, which means here is positive, so the pulse will be positive, negative real part. It means the system will positive. If we apply as input unit step function, we can get the time response as like that. What is the steady state of this equivalent? When t approaches to infinity, as you see here, this part will be 0. So the remaining part can be obtained as like that. Okay, this is the final value or steady state value of the angular speed output. So, how can we find the steady state error? We can use the same relation in here. When you put the parameters on here, kt is 1 as you see here for the unity feedback, we can easily get the steady state error as like that. What is mean for the steady state error for the with respect to the k value or controller gain? As you see here, this is the denominator value again. If the k value is increased, ESS can be decreased. But of course we have some limitation on it, such as saturation of the op-amp or the motor limitation, input voltage limitation. Okay, of course we have some limit, but if we increase the k value, we can easily decrease the steady state error. Yes, if you put the value of the DC motor on these equations, which we saw at the last lecture, okay, you can get final value of the speed as like that. Here we have a k value, controller gain. For the steady state error, you can get easily these equations. So, if you change the k value in this table, please examine it. If the k value is equal to 0.1, what we have? Steady state error will approximately 0.4 radian over second. The time response of the system is given as like that. Yes, the reference value is already 1. If you have 0.4 radian over second, as you see here, ESS, 0.6, ESS will be 0.4. It is so important difference, okay? By changing the controller gain to the 1, from 0.1 to 1, as you see here, again we have a ESS value here, which is given in here 0.0922 radian over second. Okay, what about the time constant? If you evaluate these two time constants, the time constants will decrease. We have already desired it from any controller, right? Because time constant gives us how fast the system responds to the input. The final one is if you apply K as 10, you get steady state error as like that, which is so small value, 0.0066 radian over second. So also you can decrease the time constant of the system. We can also understand the time constant of the system as like that. This is the final value, 0.6. If we multiply with 0.632, which is 63.2%, gives us the time constant. Approximately this one, the time constant on here, for example. For this system, the final value is 0.94 maybe. So we can accept as like that, for example, time constant. But for this one, which is K is equal to 10, the time constant is lesser than the others. Okay, this is the importance of the controller for any system.